Hello everyone. Today, Alperen and I will present our evaluation of the Sharp infrared distance sensor. Infrared sensors are incredibly popular in robotics and low-cost embedded systems because they are compact, easy to integrate, and provide non-contact measurements. However, their output is inherently nonlinear and can be significantly affected by saturation at extreme ranges. Without proper characterization, these limitations lead to unreliable system behavior. Therefore, our study focuses on experimentally evaluating its accuracy, repeatability, hysteresis, and effective operating range at a system level.
To understand the sensor's performance, we first perform the hardware decomposition. The unit features an infrared emitting diode IRED and a position sensitive detector PSD on the PCB. We identified key components like 1.3 ohm shunt resistor for current monitoring and signal processing ICs that convert detected angles into voltage. For our methodology, we interface the sensor with an Arduino Uno. We variate the target distance between 10 centimeter and 80 centimeter, sampling the output through a 10-bit ADC. To ensure reliability, multiple samples were collected at each point to reduce noise before transferring the data to MATLAB for analysis.
Uh, Moving to our results, Figure 1 shows the calibration curve representing the relationship between output voltage and true distance. This curve reveals the strong nonlinearity inherent to triangulation-based sensors, proving that a simple linear mapping is not sufficient for accurate estimation. We evaluated the model's accuracy in Figure 2 using prediction error. Our analysis indicates that the error remains low in the mid-range distance. However, error increases at the very short and very long ends of the spectrum due to sensor saturation and reduced sensitivity. This highlights that reliable estimation is limited to a specific operating range.
Next, we analyze the measurement stability. Figure 3 illustrates the repeatability performance quantified by the standard deviation of multiple measurements. We found low variation in the short and mid range, though fluctuations naturally increase as the target moves further away. This confirms that this sensor is most consistent within a primary effective range. We also performed a hysteresis analysis shown in the figure 4 by comparing sensor responses during increasing and decreasing distance sweeps. The results shows that the curves closely overlap. This is a positive finding as it demonstrates the sensor's response is largely independent of measurement direction or previous values. And then this is our sensor's structure, sketch and fabrication part. Uh, first one is figure 5 front view of the our sensor, and other one is the back side and the sensor board or PCB on the elements and the block diagram. This is our hardware decomposition component identification. A 1R3 resistor, its value is 1.3 ohm. A low resistance shunt resistor uses the limit and enter the current flowing through the IRED. And 153 resistors, like fixed SMD resistors. And 223 resistors 22 kilo ohm located on the left side of the PCB. This resistor is part of the output signal conditioning stage. Surface mount capacitors SMDs, a row of four ceramic capacitors that filter power supply noise and stabilize the internal circuit. And signal processing IC, the primary integrated circuit that processes data from the PCD and converts it into a distance proportional analog voltage. And PCD, position sensitive detector terminals, connection points for the optical receiver that detects the angle of the reflected infrared beam. And IRED, infrared emitting diode terminals, power and signal points for the infrared emitter that sends out the light beam. A mounting hole, an unconductive circular opening used for securing the sensor unit, the frame or chassis, and the connector pins VCC, ground, and V0. And in conclusion, our study confirms that the Sharp GP2Y0 infrared sensor is well suited for low-cost applications like obstacle detection, provided its linearity and range limitations are accounted for. Proper calibration is essential for accurate distance estimation, while it provides reliable mid-range measurements and low hysteresis. The increased error at long distances must be considered during system design. And finally, thank you for attention. Thank you for listening.